So let's briefly review like the last James talk for people was not here last week. So I motivated network coding through like two topics. One is called integer multiplication, which I proved that based on conditional network coding conjecture, integer multiplication takes omega log for constant bounding from observability. That is a very deep connection. And for the other direction, I talked about the multi-party computation. So what if the graph, if it is not a complete graph? So in multi-party computation, the classic model is you have a complete graph, you have secret channels between every pairs. And now what if the graph is not complete graph? So you can ask similar questions in this model, say, what if vertex want to learn who is the richest among its neighbor, right? And in Fox 23, Marab proved that if you assume the vertex connectivity is f log n, omega f log n, then you can do it, let's say, f secure in round of execution, which can be sub-init round. So which is quite amazing. It is tied up to Google. So yeah, so today we will see more connections to fine-tuning algorithms. Okay, so let's start. Let's first talk about this paper. In the last talk, I tried to avoid all the formal definition of network coding, but in this talk, we will do it very formally. Okay, so yeah, so let's first talk about the results. The theorem given a single source S, and it wants to so given a graph G, which can be directed, and you have a source S in B, and a subset of vertices called sinks or receivers. Note that S is a single vertex, that it S want to multicast its information to a set of vertices, right? And so this paper proves a very clean theorem, says the coding throughput. So I will define it in short. Equals to minimum of T in exact T, mean cut from S to T. So let's first appreciate in a high level way that so one direction is easy, that going through code is at most mean cut and any mean cut, because this is naturally an upper bound of the information one can send, right, from S to T, because the information received by T can be deterministically, or say is at most the entropy of the variables on the edges on this mean cut, right?
Can you define the coding throughput more?
Yeah. So yeah, I will do it in 2 minutes. So and the magic is that one can achieve the equality here. So okay, now let's do the prediction. So given a graph, and a capacity that maps address to values non-negative. So we say that a code is defined by the following components. One, you have a time. So I need the time to define the causality because there might be cycles, right? So that's the division. So I would say like in general the capacity of network coding is like the capability is even more general than this, but this is captures almost everything. So u from 1 to t the time that's okay. It's just that you want to say which edges you are considering this principle such that you is okay, or say you average t oh, and okay. So this is the alphabet that you send along this edge. Um, that's t. So to this is for any t that's that in this round you send a symbol that's from this set. Okay. Such that that you need to respect to the edge capacity. This is the edge capacity. So one need to say so I will define Tij or TUV actually. Like for an edge. For an edge TE, okay. So the size should be close to say log of this is the capacity of the loop, right?
TE corresponds.
TE is one as a thread. So UT so in each round I assuming this symbol on the edge, and you consider all the time that you send through this edge, and that the size should be what is it? AT is the size of the alphabet, like the symbol that you can send to this edge, right? So this is this saying that the upper bound on the entropy, right? Everything that you can send to this edge over all the time is upper on the better capacity.
If I just take a binary alphabet, does that is that summation?
So binary
Like AT goes to
so you mean t every AT equals to 2? Good question.
maybe after some roundings.
Yeah, so I mean it's yeah, after some rounding or say because you can always do yeah, I believe up to competencies. You can do. But with this definition, you will see it will make life easier. That you can construct the codes, whatever you want, right? Okay, and I have not finished with yes, so I space.
Also, you define UTVT as an edge, right? You define UTVT as an edge, right?
Yeah, UTVT.
But U of T plus 1 has to equal VT, right? Like it has to.
Oh no, you don't need this actually. You don't need this in this definition. Because you only need
at time t I have this edge.
so you can think about asynchronous, right? Like this the graph is you just need causality. Then overall you can first think about it is directly the cyclic graph. Does that make sense? So now I only need a causality. That's one symbol on the edge need to be computed by all the information you received previously. Right. You can of course see all the history and the function on this edge is can depends on everything. Like everything this vertex has already known. Okay.
Well, how do you enforce causality here?
Yeah, so here the next one is a causality. I haven't really so if you okay, there are several cases. If it is S, you can use the message. So the message is, let's say, okay. For now, let's think there are no in-edge from like there are no in-edge to S. Okay, one can always reduce it in this case. If it is a source, then ft is a function of omega to a t. Otherwise, f function from all the prime this is a history that we to so omega is a let's say the code has throughput okay, I was terrible with mu and h, so and field field. Yeah, so Qt is obvious that it is all the information you received before, right? All the in-edges that happens before. And so H is I define the coding throughput to be H. So if one can achieve such a code, then coding throughput is H, is at least H. Mu is a scale factor. Actually, let me see how. Yeah, so I need to move. So this is a scale factor.
Why can't you just set mu equals 1? Why can't you just set mu equals 1?
Make life easier. And I don't know, actually, I think it makes a difference.
Was it because of some wrong?
Yeah, but I actually believe it's yeah, actually good question.
So this is equality. Like,
yeah, this is equality.
for
this.
what?
There exists such mu.
Okay,
So like in the proof, one always take mu to infinity. I think that's part of the reason is the rounding. Otherwise, the you need to define a different you need a different way to define this code that each variable is not is by it will be biased. So here you always consider everything uniform. So that's why we define it this way, right? You consider everything to be uniform. So you will see that the code we construct will be with uniform distribution everywhere. That makes life easier. So right now, let's focus on the easiest formulation, right? And so that's the reason I need this scale factor. It is a bit weird. I agree. That's at the first point, like first glance, yeah. And yeah, so the whole point of the network coding is to achieve higher throughput H. So we want H to be as large as possible. We call this. So here is H. And finally, you need correctness. So you need G, oh, like for that. Yeah, so let's say it's okay. So I will define W to omega. That W is all the time that the T. So notation is a big deal. So let's say the set of things is 1, 2.
You use a different other than T. T is
Yeah. So I also noticed this. T is also used for string. Yeah, well, R. I already take out. Did I use R? That is for that VOR. Okay, that like okay. This can be weird. Okay, did I use anyway? A lot of correct. Yeah, the reason is that this was a paper in transactional information theory. Like they use even more weird notations. So I cannot translate it to like graphical with friction. Yeah, so this is a correctness that one thing can use all the information it's received to decode. And you want it to the correctness is that you want this decode function yeah, so what should I do? Such that for yeah, and actually I need to write longer than for any x that one uses framework to encode and it outputs the same math.
Sorry, what is X?
That x is the information that from S. So that one uses F to encode the information x from omega and the output should be the same as. So okay, this you see this definition is quite long and even this is like a simple version of the definition. So but the idea is actually clear. You want everything that goes along the edges to respect to the edge capacity constraint and you're sending like a variable with entropy in your h, right? And you want to maximize this.
Does this is G here undirected?
So it can be in both cases. Like some paper studies directly and some study indirectly. I think this theorem works for both. Yeah, and yeah, and that the paper we'll discuss they actually also contains two parts. Yeah. So okay, now if this definition is good, let's continue to the proof. If you have questions, feel free to ask or stop me anytime. Yeah, so one way is simple that although like if you do it formally, one need to see like upper bound entropy of the cut, right? But I believe that one can see how to do.
So that is also defined over C.
Right. Yeah. So it is
Wait,
yeah, the weighted version. Yeah. So now let's prove. first let's do an easier case. So assume G is directly and separate. A is G is equal to and then we can always give an order of the edges, right? Such that it's called topological form, right? Like such that every like all edge is always bigger than the edge. So let's label. Oh no, let's label vertex. Sorry, label vertex such that all the one so let's now consider a code defined by following as J that's that's just equal to let's say the capacity is equal. So okay now okay so in this framework every edge will appear only once in this order. Okay, it will not be so every T only contain one time slice here, and so you just define all of it like this for an edge Sj. Okay, and then for any for any pair of and for any okay the notation is a bit ambiguous. Ij is and I'm trying that this yeah, sorry for the notation that I sometimes switch it to UV or IJ, but maybe just there's some the same thing that is yeah, so why I read everything again is for simplicity that we don't need the full power of the network coding. That is only used for to prove this, right? But now we for cyclic graph we actually just need a simpler one, right? Because every edge only appears once.
Is this still proof for all directed graphs? Even like
Yeah, even cyclic. This is very general.
Okay.
But that part is not it's not hard to this is a main you already contains the main line. And for G you just map it to omega again and non-red everything again. And let's do it a little bit faster. So now I want to show that is yeah, so now I want to show the high level idea is that for any x from omega, I just want to do something very simple. That I just want to map to make every mapping a very random mapping. Like independently, I create all these mappings that for each x, you select a random element in it and you map to it. And for each ij, And for any input, I just pick a random thing. So I generate all these network coding scheme very randomly. Okay. And now I want to say
How large should I think of this method?
yeah, so now I want to claim that so for omega of size this thing, if h is so if h is equals to that the quantity, if h equals to the income, I want to prove that for eta for every eta e equals to c e times mu, such a scheme works, right? So
Two to the.
yeah, yeah, thanks. Yeah, then how to prove this such a scheme work? That is for any x in and x prime in omega, and they're not the same thing. And for any r in for anything, it actually have a different like the information it received is not the same. Then you can always decode. That's yeah, so that's the decode function I recently wrote down. So yeah, so one kind of I abuse the notation a little bit, like that's say g or x not equal to 0. Sorry. So I'm abusing notation because it actually depends on something like intermediate, right? But given x, but now let's just consider a fixed or probable, then this function, right? Like in fixed deterministic probable, then you can always do this, right? But you first by probabilistic method, you generate I want to say there exists such deterministic probable. By generating every function randomly, and there exists like a way to fix all the functions such that this claim holds. Yeah. Yeah, so now let's just relax this by epsilon constant, and I will show that for any epsilon that such code exists. Any sorry about this. Like I need to switch the notation.
Question.
Mhm.
Okay, so if I think for the graph as just just one line, and source is on left and sink is on right, and all the edges have the same capacity, then I guess the cut is, I guess maximum is just this equals to the capacity.
Right.
In this case, the I guess the symbol size would be all the same for all the edges.
Right.
Right. And then if we sample random mapping and this should also equal to the maybe the domain size.
Yeah.
But if it's a random mapping, like as long as one of the steps you have a vision, then you cannot assume.
Yeah, so the point to make sure is that you take everything to infinity. That's the collision probability. That you lose will be epsilon if you take a log, actually. That's a log.
So like you're taking you, like the graph size being 100, you're taking you to 10,000. They're one.
So just take limit mu to infinity. And I think that so the probability that that it has a collision will goes by a like 2 to the minus mu times the mu constant, and that is 1.
Wait, why? Because I thought omega would be as large as this eta, right? But then, like you're mapping from a large domain to a large domain, but the two domains have the same size.
Oh yeah, you can lose. Okay, so okay, there's a trick. That is exactly what I want to do here. Is that you first extend everything by a small small constant factor. And it takes everything to infinity, and again you can lose a constant factor.
Oh, okay.
So that is the trick. But now I actually want to conclude this formally. That's okay. That we only need to show that for any epsilon there exists a sufficiently large mu, sufficiently large that such code exists. So for every yeah, so this is a epsilon I can afford. And this is fine. And instead, let's replace omega by omega prime. So that's how I create the constant factor of the for itself.
Yeah, this is something, but you define eta to be 2 to the power c e mu. So mu inverse log to eta is just c e, right? So that inequality is trivial.
Sorry.
Like you define eta to be 2 to the power c e mu. If you plug that into that inequality, then it is just saying that c less than equal to c plus epsilon, which is trivial.
Yeah, so now I relax it eta a little bit more. Like so, okay. So this you actually ignore this now. Yeah, so that's intuitively like I want to tell you what is the scheme. Now I want to do it formally. I need to lose epsilon first, and then to solve questions. Okay, let's also relax omega a little bit, and now C to be a constant like greater than 1. And we expand omega to omega prime for that function and for any function. So now let's take the event fx to be 1 if everything any GLX goes to for all the for any and 0 otherwise. So fx equals to 1 means this is a good event for x, that every single successfully decoded event. Right.
You mean, but GL is it's not sampled. It's going to depend on the random outcomes.
Yeah, so this the randomness is you sample all the functions.
Do you just mean like there's no collision of X and stages?
So no collision. If no collision, yeah, this is one.
Okay.
Yeah. So but they are not exactly right. Like so, this is I mean, once you correctly decode X everywhere.
Okay.
Yeah, but if there are no collision on everywhere, then this is
fine.
definitely correct. But sometimes there can be collision somewhere for other things.
Oh wait, how do you define G?
Yeah, G. So the way to construct the networking scheme is to randomly sample every function here, right? So G is a function. G is a decoding function.
Is G sample? G is
G. Oh, yeah. Sorry, G is not sample. Sorry. Yeah, you are right. Yeah, you are right. So G is not sample. So yeah, good question. So yeah, I want to say no collection in the receiver's view, right? Yeah, let me redefine this. Uh, yes, just let me build the notation. Uh, right. Are there any better ways to do this? Or we can define like ZL. ZL is a symbol it receive, then it will be similar to that. Or it will be precise. So CL X goes to there's no collision for any movement. Or okay. So this is the is yeah. Thanks for the questions. Um, and now okay. Now let's fix fix one X and L. And now let's consider X prime in omega and let's define the set of collision. Okay. So for any X prime, let's define P0 is a set with no collision. And B1 is that they have collisions. And I just need to show that so the event that the collision happens for thing is small. So what is the bad case? The bad case is the probability that that there exists a peak. What is bad is for some B in B, S is not in B. So the probability is 0 equals to B. Wait, S is in B. And there exists some RL not in B. Okay, P is a set with no without collision. And you want to upper bound the bad event. That for any B, you want upper bound the probability that such B0 equals to B event, right? So in this case, there will be some collision on RA, which is bad. And you do a union bound after that. Okay. So this equals to probability. And just the upper boundary first. Okay, what is this term? So I think this term is that all the edges from B to outside is bad. That a collision occurs, right? Because there is no collision in B. And so this is the equilibrium condition on. And you want collision happens everywhere outside. So like every edge on this card should be bad. So this will be IJ, I J not IJ. Yeah, this thing. And what we assume is that we gave us a epsilon relaxation. So that's how you create the relaxation. So right. So now because you so let's first write down this. So because epsilon is an absolute constant, so you can also create like a eta sigma. How to write okay the zeta, right? It's in zeta. How to write zeta? I'm pretty bad at writing Greek of it.
You draw a fish and then you draw an S.
Oh.
You draw a fish. Yeah, there you go.
Okay. Okay. Yeah. So there exists a zeta larger than 0 such that this holds, and now this probability will be of let's just say this is a crossing here. Okay, yeah, does this make sense? You just plug in here. And now, so here you have, so now you need to consider using the union bound. Okay, just one more step. So this is you have some CIG together. It is a mean cut, which is H by assumption, or at this stage by assumption. So this is H plus this constant, right? So the summation of CIG is at this stage, right? Because H is by assumption the mean of the mean cloud. And now I think we need to do union bound from here.
I guess you lose a factor of n squared. I think.
Yeah, it's something. Sorry.
I mean, like I mean, then I will also lose a factor of not practice for this. Like you sum over CIJ plus theta. CIJ sum to H, theta sum to.
Oh, right.
Oh, it's okay. So that can be something.
Yeah. So. Yeah, one indeed lose, but I think this is also a typo in the paper. It's fine. I mean, this is okay. Yeah, if you take mu to infinity, I think everything doesn't matter.
Yeah.
And now we need to show Yeah, so a valid event happens if probability that the LX was equals to X prime is at most 2 to the B. So this is a valid event for a specific pair of X and X prime. So there are like 2 to the B numbers of B, and then valid event happens with this probability. Um, and then further, you also need to take a take the unit bound for every X prime, right? So if this holds, what is the probability this holds for? So this is a for specific X prime. What if this holds for arbitrary X prime? You need to take another unit bound, which you lose another factor of 2 to the mu h, because there are that many X prime, and these two things cancel out. And what remaining is 2 to the b times 2 to the minus mu times zeta. I'll take mu to infinity, and this will be something goes to 0, right? And so to infinity, so this will goes to 0. Right. Okay. I think now I finished the proof for this PhD. Any question? Did I miss something? Actually, let me think. Yeah, because epsilon can be any constant greater than 0, and c can be any constant greater than 1. So you take the limit again, and that proves.
So wait, the decoding function is just like the identity?
No, the decoding function is that even such condition does not never happen. So you can always so there always exists.
Oh, they're existing, but it's not
Yeah, so-
efficient or something. You don't really care. You don't care about computation at all. You're saying.
Yeah. For here, we just want to prove the existence of results. And I think for in general, linear method coding exists. So the follow-up work, like 3 years later, like they proved linear code suffice, and then like polynomial time algorithm exists.
Okay.
Yeah, sorry about the notation. That it also confused me a lot. Okay.
So then the encoding is you're choosing something random. The encoding is you're choosing something random.
The
Because
encoding.
all you care about is existence again. So,
Yeah,
okay.
here is by probabilistic method.
Yeah. Do you think if you choose random linear, it also works?
I think so. I
Okay.
think that's how they prove linear code suffice.
Okay.
Right?
But random linear is hard to decode.
Right. Okay. I didn't follow that
Okay.
work a lot, but yeah, that's actually an interesting question, like how they do linear code. Yeah, but actually the second paper I'm presenting today, which I don't have much time, but I think that is I'm not that simple as this one, because that is algorithm paper. This is coding like paper. Yeah. So now let's start with the second. Oh, I only finished PhD, but I think for second graph is you do a like time expanded graph like that. Now you need the full power of the network coding. So I will not do the full proof for general graph. So, but the idea is that you create say infinity level of this graph, right? Like for there is a time that for any time t, all the edges goes to t plus 1. And for a thing, it collects everything it's received along all the history. So that's how you prove general graph. Yeah.
So you're turning it into an infinite DAG.
Yeah, infinite. That's it. Yeah, but I think the beautiful idea here is actually random encoding works.
Right.
yeah, so yeah, I don't have much time as much on leave like
You guys have
30. Yeah, so let me briefly tell you about the idea of how you apply this uh to the fine-grained algorithm. So a brief introduction to operator connectivity. If G is undirected graph, then everything is very easy because nowadays people know how to compute log equal tree in almost linear time. This takes this time for undirected graph. So this the problem in undirected graph is not that interesting because that is almost the same as computing one ST S over. Right. The problem of operator connectivity is very interesting in the directed graph. So one trivial algorithm, like algorithm is this type. That you just compute every pair by calling a max flow or and then one can improve this to run to the omega. So this using the idea I presented today. It's using some natural code. So this is
this where you use the linear part?
yes,
Okay.
yes, this is a linear, yeah, like exactly the thing we just described. And for K, for bounded operator, this can be done in K to the omega. Yeah, so omega is the measure, n to the omega is the matrix multiplication.
So what is K? What is K?
So if you only care about like the pairs with connectivity at most K, then that suffices. That's you for ST that the connectivity is larger than K, you just output okay, this is larger than K. I don't need to compute the exact value.
Why is it taking more time? I think.
Yeah, why?
No, that's better. That's n versus n.
Oh, this N. Oh, this.
Yeah. So
Oh,
K
okay.
n to the omega. Yeah. So this is not always better than that. So this is for dense graph. I believe this is better. But I think this yeah, so that's you need to compare them like carefully. It's not always better. So this is a Fox paper in 2011, and this is a paper in called 23. This is the journal version is 24, and this forgot the others. Yeah, but let me try to give a high level here very quickly. So the idea is using linear network coding, like random one, like how we generate the encodings in here. That given like for any source S, you just say you put random vectors on the outgoing edges, right? And you just for each intermediate product, for each outgoing edge, I just take a random linear combination of the input. That's it. That's the whole thing. And you generate, say, okay, everything is on a larger enough. Let's say P is n to the fifth. Okay. And now for T, I only want to see the dimension of the vectors, the in vectors. And I claim the dimension with high probability it is the ST connectivity. That dimension of this subspace.
So for the vector on the edge, the dimension of that vector is the capacity of the edge.
Sorry.
Like the random vectors on the edge is that.
Okay. Oh yeah. Good question. So that's take dimension to be
Isn't that the dimension of vectors on every edge is the same and we're talking about dimension of a subspace and
So so dimension, I think doesn't suffice, right? Like, but I think if you, okay, it depends on which version that you compute. Here,
Oh, wait, is the
here
graph,
it is k dimension k.
is the graph with,
No. So
Oh.
yeah, that's important.
Oh, it's
Everything
not-
is unweighted.
oh,
And I think for these two versions, they are different. So this one you take dimension k for everything, and this one you take dimension for everything. Yeah, so that's the difference.
Wait, why does the weight matter for connectivity?
Sorry.
Why does the weight matter for connectivity? This is connectivity problem, right?
Yeah, because here you just count dimension. That's something is unweighted. Right?
Oh, you're saying
Dimension-
K, like if you
Everything
care
should
about
be
weight.
unweighted because here you just count the dimension. I don't know how to do it with like.
No, what's the weighted version of the problem? I'm just confused. The weighted version of the problem is that like the weights of the paths need to add up to K, is that what it is?
Weighted, of course, you can define connectivity, right? Like the weighted income
Oh, okay,
from every pair.
okay.
So yeah, that's a good question from Huasheng. That dimension of the thing you generate here. So that's how that's how we see this difference, right? Like you can have like so for large enough dimension, so you can
So can you write out the algorithms? There.
yeah. So the algorithm is that two matrices L and R. For this, let's just define this one. L and L is n times Kn matrix, and R is Kn times n matrix. And for each edge, the vector on it is a summation of I and K, and the summation of that is in edge of this view, right? It's supposed to be nav is in of view. The matrix have no um so this is a like low dimension linear combination of the in vector. Therefore, okay, sorry. Let me correct. Everything is still with linear dimension, but you do low dimension combination. That you first like map it to a low dimension, and you combine it.
oh, it's a simple thing.
So what is that one? So F is say the in edge of this. It's pretty cool. Yeah. Oh,
Yeah.
sorry. You might you can need that office.
And we found
Yeah.
this
Yeah.
Okay, so you're choosing F randomly and then L and R from the algorithm?
So so the algorithm is yeah so for this ST connectivity algorithm you consider generating this randomly, and you can do the random thing, right, and count the dimensions. But this is just a subroutine in that
Okay.
yeah. But do you agree with this? If you
Okay, so I'll just say something about it. So L is an n cross K matrix. So for every edge you generate a k dimensional vector, we take them as rows and that is a n cross k matrix. And similarly you generate R and this is somehow used for like encoding and decoding at every vertex, right?
Yeah, sorry for this confusion that each edge here,
Okay. I see. Makes sense.
I think each edge here is
Yeah, so this is exactly the same as your other proof, except the maps are linear now, right? Like that's the only difference.
yeah, but give some intuition, yeah. So
I mean, this is you're just picking a random linear map, right?
yeah. Okay.
And they're fixed.
So
when you have
every
your-
edge here is dimension k, right? Let me think. What is this?
Actually, I think you have to pad it with zeros.
Yeah, so that's my question. Like, do I need to make them dimension linear or just linear? I think that we need to make them linear. But the inference dimension is k. So that's the point. Yeah, that's a point I know how to fix.
So you have at most 10 neighbors.
Yeah, so do you agree like inherently this is dimension k, right? Inherently, because I for any u, so these things are always the same. You just do like linear like k dimension linear combination, right? So inherently it is dimension k, but you still need dimension n for flow vector. See?
So what is on every edge, vector or matrix?
Yeah. I would say like I don't understand linear code very well after presenting this.
I'm just, it's about the.
Yeah.
So on every node, you generate, a random element.
Flow vector.
No, I think the Eleanor are fixed
Like,
throughout the entire algorithm.
for every vertex, and then.
Yeah, they just pick one at random at the beginning, and then for the source they pick a random set of initial like vectors to go out of it, and then they update the vectors using this equation. And you're taking a linear combination of k things, and the hope is that this parallelizes the k paths that you're trying to track. I think this is my intuition for what's happening. And information theoretically, this sounds like the right thing, right? Like,
But what is the dimension of flow vector here? I actually confused.
oh, of f.
Yeah, I actually confused.
It should be
Because f is in E in.
Yeah, K,
It can
yeah.
be adjacent to at most n things. Each of them has a dimension case of kn. And whatever you don't have, you pad with, you know.
I think kn, right?
Okay. Let's say like for large enough dimension, this works. Okay. And now let me just finish the whole algorithm.
I mean, it should be kn just by this, right? But by the fact that the bound is kn to the omega, it should be kn, right? It should be kn, right? Because since the bound is that, like, if it was m, then it would be too big. It wouldn't hit that bound, right?
Yeah. But yeah, actually I don't know.
Okay.
Let me just finish the argument. I think that just need this intuition actually that the algorithm doesn't compute this. So you just generate a random L and R like in FB with this dimension. And now I think that so let's say let's consider the network calling the algebraic approach that F is a like times one matrix that have a assigned flow field elements, and then this is equals to so the matrix of K, so K and plus C. So C is like the initial thing that you would generate. Okay, and this thing, so I think if you solve this, and you call this matrix then. And there's a theorem proof that the matrix, the sum matrix of this thing at E out of S and E in of T. So this sub you only need to consider the rank of this sub matrix. And that equals to lambda S T the power to T. But intuitively, this is a bit high level intuition. And now, as long as this like preserve the yeah, thanks for coming. Yeah. As long as it preserves the dimension of like the dimension, you can preserve the dimension up to lambda S T. So that's a high level intuition. And that's the reason you have an omega there, because you are computing the inverse of the matrix. It's just computation. Yes. Yeah, let me figure out this later. What dimensional that should be. Yeah, but here you can see like you don't need to compute this at all. Like you just need to say generate a random LR, and you compute this thing like the inverse of this matrix. That's it. And this can be computed in either this or that time, depends on the dimension.
Okay, so when you wrote F equals KF plus C, you like vectorized these equations, and you said, okay, now I'm going to stack all the E's into one matrix, and then I'm going to like what you did is you put like you wrote that's one vector in terms of the other flow vectors, right? So now you stack the equations together. You're saying.
You mean this one?
Yeah.
This equation, yes.
Yeah.
That you stack. This is you stack this equation.
Right.
Everywhere
Okay.
that you derive this thing.
Nice.
Yeah, thank you for coming.